talk about smart materials for protein crystallization. Over to you, Naomi.
Thank you, Jonathan. Before I go into the subject itself, I'd just like to explain in briefly why we want to crystallize proteins in the first place. Because proteins are the major machinery of life, they are the targets for new and improved medicines. And the functions of proteins is determined by their three-dimensional structure, and therefore knowledge of this structure enables rational drug design. X-ray crystallography is the most reliable method to determine protein structures, but it is totally reliant on crystals, and hence the expression crystal clear. Obtaining diffraction quality crystals is a major bottleneck to progress, and that is because these are very large molecules. Crystallization is a multi-parametric process. Most proteins of interest are limited in supply, and they're sensitive to external conditions, and that's why harsh methods which are used for other materials, such as diamonds and small molecules, are precluded.
This is a demonstration.
Protein crystals are, because of their sensitivity, they need to be persuaded to form crystals rather than pushed to do so. The state of the art these days is showing how all the major structural genomics projects have been trying, with a lot of investment, to crystallize as many proteins and solve their structures. And we can see results started coming in 2004, and still in 2016, the success rate has remained quite the same. We are not above 20%. So we've got to tackle this problem. And the main problems are that we're getting either no crystals at all, we're getting tiny, low-quality crystals, and most frustrating, we're getting often large, beautiful crystals that do not diffract a single spot. So what this talk will present is some practical solutions. And I want to show the ideas and the inspiration for them, the rationale for doing what we do, and show some examples of successful results. Nucleation is the key to crystallization. It is the conception of crystals, and therefore the ability to control it would give us a handle on the whole crystallization process. The most common way to nucleate crystals is by seeding, and there's a variety of ways to do it, but all this requires crystals to start with. And what do we do when we don't have crystals? And in that instance, we try what we call nucleants, and they are non-protein materials that induce nucleation and formation of crystals, and we want them for two purposes. One, to have crystals at ideal conditions, which will give us improved crystals, and the other is as a means to maximize the chances of obtaining crystals in the first place. And there's an ongoing search for what we call a universal nucleant, something that we'd like to sprinkle into any trial and get it to crystallize. Now, this is very ambitious, but we are trying. There's examples of nucleants over the years. Nucleants have been dealt with already from 1988, and there's a whole list here which I won't read out. And these have been successful to some extent, but not enough. And in 2001, we thought of a new approach completely to designing nucleants, whereby to use porous materials with cavities the size of protein molecules, which is around 5 to 20 nanometers on the standard proteins. And the rationale for this was that the cavities in the porous materials will attract the protein molecules towards them. And once several molecules are trapped, they will form the nuclei, nucleation, which we were talking about the first step, and other molecules from the solution will migrate to the nuclei and pack to form crystals. And we tried a variety of things, porous silicon, nanoporous gold, carbon nanotubes, which all worked, but again not to be called a universal nucleant. They worked on some proteins, but not on others. And then I heard of a professor at Imperial College called Larry Hench, that he was doing using something called bioglass for regeneration of bone tissue. And he used porous materials, but the size of millimeter or centimeters. And I called him up, and he didn't know me at all. I said, Larry, can you make me a bioglass with pore sizes with a distribution between 2 and 10 nanometers? And he said, yes, I can. And he did. And I put it into crystallization trials, and this worked very, very well. That crystallized more proteins than previous nucleants had done, and it got commercialized under the name of Nomi's nucleant. And here is just a few examples of crystals that crystallized on this nucleant that couldn't crystallize otherwise. And when you look at the picture, you see crystals sort of coming out of a sort of fluffy bit, and this fluffy thing is the bioglass, the Nomi's nucleant, and this is under the microscope. It looks like a bit of a sponge. In real terms, its size is about 100 micrometer diameter. And this, we were saying about universal nucleant. Now, of course, until you've crystallized thousands of proteins, you can't say it's universal. But what this table shows is that it was used for a variety of different proteins with different molecular weights, different precipitants, a wide variety of pH, and worked for all of them. So meaning that it is likely to work on many things, not just limited. Now, this was all very nice, but two things were wrong with, not wrong, but two things were limiting with this bioglass. One is that it is manual. You have to do the experiments manually. You have to take one grain, like a grain of salt, and put it into a trial. And the second thing is that it had no special affinity for proteins. It was mechanically, the success of it was a distribution of pores, whereas the protein molecules sort of fell into the pores rather than because it attracted protein as such. So we were really thinking of something that we knew that pores are important, but we wanted pores that will have specific affinity to proteins. A new idea came about when searching for such materials. I heard about materials called molecularly imprinted polymers, or MIPS for short, which had nothing to do with crystallization. MIPS are polymers formed in the presence of a molecule that is extracted afterwards and leaves behind cavities imprinted with that molecule. The cavities in the gel retain a memory of the molecule after it is removed and exhibit highly selective binding of it. Now, the molecule can be any molecule or can be a protein. And then it occurred to me that such materials enable us to harness proteins as templates for producing their own crystallization. And looking for such materials, I heard of Dr. Sab Reddy at Surrey University, who was working with molecularly printed polymers for biosensor research, nothing to do with crystallization. So I called him up and I asked him whether he can imprint his polymers with some of my proteins of interest, which he did, and I tried those in crystallization trials. And then together, they come together, and if you put a cross-linker, then polymerization takes place, and you get a gel with a protein embedded in it. And then when you take the protein out, the cavity remains, which remembers the protein. So we started with a screening process, because as I said, we wanted two things. We wanted to know, will we get crystals in cases where we won't get them otherwise, first of all. And the answer is yes. We see here these are target proteins, all of them, and we see that we get crystals. If you look at the picture, you see that the kind of gooey shadow in the picture is the MIP itself, and the crystals are around it, obviously. The color is blue. So we got it in these are three cases, but we got in more where you get about 8 to 10% more hits in the screening than you would get otherwise without the MIPS. Now, even more interesting was the major improvement in crystal quality. We got an HIV complex with 3 proteins in it, and which initially, by standard methodology, diffracted to 9 angstrom. Now, 9 angstrom is as good as no angstrom. And the crystals looked good. Like I was saying, they looked good, you thought you get the diffraction, and no, nothing really. And then, if you crystallize it in the presence of MIP, you get a diffraction to 4.2 angstrom. And another example is human migration inhibitory factor, where you see the pictures with the arrow pointing to the gooey stuff. Here is the MIP, and the single crystal, nice single crystals well diffracting, and the control with the same polymer but not imprinted with the protein is giving you just a clear drop. Now, of course, the proof of anything is not in the nice pictures, but in the diffraction. And this table shows all of them target proteins, and if you look at each and every one, the diffraction is better with the MIP. And we could not get it as well without the MIP. Here I won't go into details of this table, just to show that we did hundreds and almost thousands of experiments with all the MIPs, using cognate MIPs and MIPs which are a bit different but similar in molecular weight, and wanting to see how the efficiency of these MIPs worked on different proteins. And in summary, we see that the MIPs, which are also called smart materials, they produce hits that would have been missed in their absence. They produce higher quality crystals. And very interestingly, it is not imperative to have a cognate MIP. You can use a MIP of a similar molecular weight of one protein to crystallize another. Now, the original MIPs, which I've been telling about, were put into trials by hand because the original MIPs were the original MIPs which we have just described. No, not which we have.
Yeah,
Start again.
So start again,
Yeah.
anytime, yeah, when you're ready.
The original MIPs, which I just described, were viscous gel-like materials that could only be dispensed manually. Nowadays, most laboratories have got automated robots for crystallization and are doing high-throughput trials, and nobody is keen to do manual trials if they don't have to. And therefore, we had to design a new generation of MIPs which would be compatible for dispensation by robot and high-throughput experiments. And we have managed to do that. We have now got MIPs which are liquid in consistency, and they can be easily dispensed with all the other crystallization ingredients by any robot. Another important thing about the MIPs is that they can be used in very small quantities. The MIP has only got to be 10% of the entire drop. So if you're using 100 nanoliter or 200 nanoliter drops, it's enough to have 10 or 20 nanoliter of MIP in it. And therefore, 100 microliter is sufficient for more than 5,000 trials. And the next stage was to commercialize the MIPs. And a product is now available, which is called Chain Ready MIP. And this is commercialized by Imperial Innovations, who is here with us and will tell you more about it. All this research takes many years, and many people were involved, and I would like to acknowledge the people involved with these experiments and results.
Thank you very much. I'd now like to hand over to Johnny Gibbons, who's an associate at Imperial Innovations. Johnny will be telling us a little bit more about what Imperial Innovations do and how they brought Chain Ready MIP to the commercial space. Over to you, Johnny.
Yeah, thanks. So Imperial Innovations is the technology transfer company for Imperial College. So it's our job to help academics to commercialise their inventions. We do that in a number of ways. One is by sort of financing, patents, proof of concept, marketing, helping set them up with early stage investment, so angel investors and so on, helping just advise the regulatory side as well. And we have a number of routes really which we use to commercialize. So some technologies are licensed, and so in other words a company will come along and they will ask us, oh, can we use this? And we'll sort of give them permission to do so, and they'll pay us royalties for that. Another is spin-outs, which I'm sure a lot of people know about from sort of, I suppose, Dragon's Den or whatever. And the latest one that we've got now is an online catalogue called QuickTech, and MIPS are marketed through QuickTech. So this is an online product catalogue, a bit like Sigma Aldrich, but much smaller scale. And we're using it principally for materials that can be used in research. So like MIPS, sort of antibodies, cell lines, also stuff like software. So it's anything that can just be provided. I think the important thing for so academics listening in to this is that pretty much every university has its own technology transfer office or company. So it's important for you to know that they exist, and to know that these are the guys you should be talking to if you have anything that you think you want to sort of bring to market. In terms of what we decide to back, it's really all about what we would call a value proposition. So it's basically saying, is this technology that you've developed or material that you've developed, is it better than the next alternative? Is there another alternative? Is somebody going to be, is it going to save somebody cost? Is it going to save somebody time? Because if so, then it has a value, and that is its value proposition. And so that's what we apply to the technologies that come in to decide whether to take them forward or not. And I mean, really, the technologies that come in can really be anything. They can be designs, they can be things that are patented, they can be materials that people have developed. There's often not really a sort of time scale either, because for something which is patented or is a design, it's committed to paper, so we can continue to commercialize that, sort of years after the academic has retired or moved on or whatever. And a lot of materials also tend to be sort of deposited somewhere, either in the university or with a third party. So again, you might make a batch of antibodies 20 years ago, and if they're still kicking about in a fridge, then, and somebody's interested in using them for research, then it can be done. And I mean, really, the reason we exist is for impact. We really want to make sure that the things that are developed in universities get out there and they find a use and they advance research and they bring benefit. So I mean, I'll just sort of finish with some of the challenges really that we face when it comes to sort of commercializing things, because once we've made a decision that we're going to back it, that's based on how we feel we can actually bring it to market. And essentially the decision behind that is can we sort of recoup our costs, and does it make sense to do this? And so with MIPS, MIPS has been patented. We're selling it through our online catalogue, as I mentioned, and really this is about, first of all, promoting it, letting people know it's out there. So the fact that we have it online, it's sort of easily searchable. We've published an article recently in Rigaku, but Naomi herself is the biggest asset we have really on this. She's, as anyone who's ever met her, extremely enthusiastic. I'm sure at crystallography conferences, she's the life and soul of the party, I'd imagine. She's really out there talking to people. Lots of people sort of come to her for this product, and it's her personal network that's worked it. And actually, for a lot of academics who are working in quite niche areas and have quite niche products, that is really key. They know a lot of the people who are ultimately going to be interested in it. So finding what those things which we would call sort of marketing channels really is, I suppose, the biggest challenge for all the technology that comes through us. But I think the important takeaway message that I would like to leave academics here is that there is always somebody you can talk to who can help you with these things. There'll be somebody in your university who can do it, and anything that you have may well, if it saves somebody time, if it saves somebody money, then it has value, and you can use that to have an impact on somebody else's research. You can use it to sort of raise funds for your own university and for your own research. So it's it's absolutely sort of key that academics are engaged with their technology transfer people, because they can get real benefit from it.
Great, thank you very much,
This was
Johnny.
superb. Excellent.